Mixers are used in transceivers both as down converters, as we can see here in this schematic, or as up converters in the transmit chain. Ideally, we can describe mixers as multipliers, multiplying two cosine circuits. So here we can see a description of an ideal multiplier. So we have an RF frequency that is multiplied with an LO frequency, local oscillator frequency. And if we just do the simple multiplication, we will get two new frequencies. One will be the difference of these differences, and the other one will be the addition of these frequencies. And this is how we do up and down converting. So if the RF and LO frequencies are such that they're close enough, we will be able to convert the signal with this part of the expression to a lower frequency. This would be a down converter. We can certainly do an up converter with the other part of the expression. And when we talk about the spectral behavior of these frequency converters, so we can think about the RF frequency, and next to it we have the LO frequency, and we want to convert it to maybe a lower frequency, but we always need to remember that there's an image frequency that is the same distance from the LO frequency that can be converted into the same IF or intermediate frequency after the conversion. And it can actually degrade or destroy the actual signal we are looking at. So we usually will need to filter it out to make sure that we don't get two multiples of two different frequencies at the same intermediate or IF frequency as an output. Starting with the passive mixers, we will use them in CMOS design mainly because CMOS transistors have excellent switching behavior. So passive mixers are very well suited for CMOS design. The input and the mixer is current driven, so we drive it with currents, and we actually mix currents, and we will touch it later on. It is very simple design usually, and very small size if we only consider the core of the mixer. To the core we need to add, of course, local oscillator buffers or amplifiers, which will further complicate the design, but we only look at the mixer part. The core part is very, very simple, small in size. If we look at passive mixers, usually they are very broadband by nature. They are very linear compared to active designs that we will discuss later on. They perform mixing with low 1/f design due to very low or no DC current flowing in these transistors. And it would be critical to have low 1/f noise, especially in direct conversion mixers. These passive mixers, they usually don't introduce any gain, but rather power losses that we need to minimize. So this is some of the negative behavior of these passive mixers, is the loss that we have. And they usually require high amplitude local oscillator or LO buffers. And this will complicate the design. We said the core is very simple, but the LO buffers will need to have higher gain, higher output voltage, so the buffers will become more challenging with passive mixers. And the other, maybe last point I want to mention about passive mixers is that they are very simple, but they provide no isolation between input and output. And this is another maybe negative attribute to passive mixers. We will compare it later on to active mixers that do provide some isolation, which we would like to have in many chain or circuit circumstances. When analyzing a passive mixer operation concept, we start by analyzing a simple switch. And we assume that there is an input signal, M, that is being switched on and off by a local oscillator and generating as an outcome the RF signal. Or in a very simple expression, the RF signal in time domain will be the multiplication of the LO signal times the input M. Now, if we assume on and off switching, the simple, most easy way to analyze the circuit is with a 50% duty cycle square wave. And this 50% duty cycle square wave can be described by its Fourier series. And this Fourier series will have a DC component, and it will have all the odd frequencies. So first harmonic and third and the fifth and so on. And then we can go back to find RF in time domain, and it will have, actually it will be this expression, where this expression we see the input signal M multiplied by the different odd harmonics of the local oscillator. Usually when we look at mixers, usually we will focus on the multiplication of the input signal with the fundamental frequency, but there are applications of subharmonic mixing where we will take one of the next harmonics. However, this was treatment for an ideal square wave LO. In the next slide we will see what happens when the LO is less ideal than 50% duty cycle square wave. What happens if we have a practical LO rather than an ideal LO? So the practical LO may be such that it will have some transient on-off time, or it will not be exactly 50% duty cycle, or both have transient and non-50% duty cycle behavior. And these two new waves, or slightly different waves than the square wave, will generate even harmonics. So if we look at the Fourier Fourier series of these two signals, or a combination of them, it will have even harmonics, like second, fourth, and so on. These even harmonics are parasitic harmonics. We usually really will try to get rid of them because they are closer in frequency to the frequencies that we are looking after. But they will have usually a lower amplitude than the first harmonic for sure. And depending on how long will be these transients, or how far from 50% duty cycle will be this amplitude. And we will later on see how we can minimize these even harmonics in designing a balanced mixer. In this slide, we can see the spectrum of a switched NMOS transistor. So this is a real transistor, not an ideal switch that is being switched by a more physical LO. And let's check the spectrum behavior of this transistor. So what we can see here, we can see the first harmonic, third and fifth being more significant than the second, fourth and the other even harmonics, which is explained by the more square wave 50% duty cycle nature of the LO. It's not an ideal LO, but it's still very close to ideal LO. So the second harmonic is lower than the third, and so forth with the fourth compared to the fifth. However, we do have these harmonics. They're noticeable. When we do the conversion, we see that we take a low frequency signal and multiply it or switch it with a high frequency LO. So we get the sum of these frequencies, the LO, and the difference between these frequencies, this input and the LO. So we have both sidebands, upper and lower sideband, but we do see the LO frequency itself leaking in the spectral picture, which is a problem. It's a major problem. Because it can saturate the transmit chain or the receive chain. We didn't see this product, the LO product, in the mathematical expression because it's not really coming from the switching behavior of the transistor, but rather from coupling, capacitive coupling between the LO port, the gate, as we will see soon, and the output. So just because we have some capacitance between LO and output, the LO signal is really leaking out, and it continues with all the other harmonics. So in this picture, there are two things that we will try to improve later on. One is definitely the LO leakage. We want to minimize it. And the second is the even harmonics that, even though they're low, they're not low enough for us to be safe when we design full receivers or transceivers. In this slide, we can see the simplified schematic of a NMOS transistor being used as a switch. At the input, we have a signal that is noted as a VBB, as a baseband signal, and the output will be in RF frequency, and basically we are turning the gate voltage high and low with as close as possible to a square wave. The biasing condition to this transistor will be such that really the VDS, V drain source, is 0. So there's no current flowing in DC between the input and output. And the V gate source, and actually it's also the V gate drain, needs to be very close to VT, the threshold voltage. So when we just add here the square wave, the LO signal, the AC or the RF LO signal, when we just introduce it, we have either higher or lower than VT voltage between gate source or gate drain, and this really opens or closes the NMOS that is being used as a switch here as fast as we can. Okay, so really gate biasing is very close to VT to achieve this performance. Now the transistor, since it has just a threshold voltage and no VDS, it really operates in the linear regime of the transistor. And here in the ID/VT curve, we can see where is this um, area of operation that the transistor is operating in. And basically we are switching the gate voltage, and we are moving from a very high drain source resistance to fairly low, couple of maybe not ohms but tens of ohm, maybe 20 ohm, 30 ohm. It is hard to get to much lower resistances between drain and source, because this will actually require us to increase the transistor size. And if we increase the transistor size, then we will introduce higher capacitances that we already know increase, for example, LO leakage. So we don't want to use too big of transistors here. So basically we switch between very high resistance, drain source resistance, to fairly low compared to 50 ohm, but it can be, as I said, 20, 30 ohm resistance. Values for series resistance for the on condition. In previous sessions, when we talked about LNAs and power amplifiers, we have introduced differential or symmetrical topologies. So there's a motivation to do it also with mixers. With mixers, we have even more motivations to do a double balanced design. And actually, even in the old days where people used single-ended mixers, they had internal balloons to really have double balanced performance, just to improve LO leakage performance and further reduce the even harmonics generated within the mixer. But in balanced design, we don't need to use, or in differential design, we don't need to use balloons anymore, but we do take care of the double balanced topology. So this topology has the input signal connected between these two nodes. It incorporates 4 NMOS transistors, where the LO signal is connected to this pair, and the complementary LO signal connected to this pair. So we are switching on these two signals, and then these two are off, and then vice versa. 50% of the time we have these two transistors on, taking the input signal to the output, which is here, and the other 50% of the time these two take on and these two are off. And usually, as we mentioned before, we will try to get the LO signal as square wave 50% as possible. Now, as I said before, we will see soon that this balanced performance and balanced topology is a good way to improve LO, local oscillator leakage to the output, and also to further reduce the even harmonics. Analyzing the performance of the balanced mixers, we need to look at the output, and we said that these mixers are current driven. So basically we are switching currents here, and the output current will be the difference between I1 minus I2 minus I3 minus I4. So we have M1, M2 and M4 and M3 here, and the output current is described right here. What we need to see is, because of the different phases, is that I1 is same amplitude but different phase than I3, and same goes with I2 and I4. Now, if we look at I1, we have derived before for a non-ideal LO this expression, okay? And if we look at I2, because of the relative phases, I2 will get this expression. So we have different signs between I1 and I2 on the odd frequencies, and same sign, negative sign, for the even frequencies. So when we subtract these two, we get rid, theoretically we get rid of the even harmonics, where we are doubling the odd harmonics. So in summary, N odd for all the odd harmonics will be 4 times I1, because we get the same behavior with I3 and I4 as we got with I1 and I2. And theoretically, all the even harmonics will be zeroed out. Of course, practically, we cannot really zero the even harmonics, but we can really reject them depending on the layout and the symmetry and repeatability of the transistors to maybe 30-40 dB down, which is quite significant. This treatment, theoretical treatment, does not explain how the circuit improves the LO leakage, but it was the same before. The mathematical treatment did not explain why we get the LO leakage on the first hand. So let's try to touch it right now. So why do we have a LO leakage? Because we have an LO signal here and we have some capacitance between the gate and the output. Okay, so in non-balanced designs, we get LO leaking into the output. However, if we look at this design, we have on this gate we have the LO signal, and on this gate we have the complementary LO, or the negative of this signal, and they're both leaking at different phase to the same output. So by leaking at opposite phases to the same output, they balance each other, or they cancel, or effectively they reduce the total LO leakage at the output to be very, very low. And when we talk about very, very low, we also get figures of close to 30 to maybe 40 dB lower than it used to be with a single switch LO leakage. So that's the way we improve LO leakage performance. Looking at the spectral performance of a double balanced mixer, and repeating same or similar simulation conditions with real physical transistors biased correctly, we find the new spectrum, and we can try to compare it to the spectrum of just one switch. So we find that we get the fundamental, and we get the third harmonic and the fifth harmonic and so on. But what happened to the even harmonics? They are really rejected much lower than they used to be before. This is a theoretical picture, because it does not take into account layout differences that may still have some effect on the second and fourth harmonic, and also it has some effect on the LO leakage. But let's look at the new LO leakage. The LO leakage here with this, let's say, not ideal but improved conditions, is really much lower than the information itself. And this is how we want our mixers to perform. So in reality, because we have some non-ideal layout and some more differences between devices, they're not fully matched, Maybe we will not get this improvement, but as I said before, we will definitely get to 30 to 40 dB improvement on LO leakage. And this picture is actually very much explains the qualitative improvements we get from the double balanced topology. Thank you for joining me to the session that started the mixer subject. We have covered passive designs, and in the next sessions we will cover active mixer designs.